Hello everybody. We are now going to work on part 2 of the rotational motion of chapter 8, and this is the final part of the chapter 8 and actually the final chapter for us for this physics 151. So finally we made it towards the end. So far in rotational motion we covered 3 rotational quantities. We talked about angular displacement delta theta, which is also a rotational quantity. We talked about omega, which is actually radial velocity or also called angular velocity. And then there is alpha, which is also called angular acceleration. And then we went ahead and talked about similarities between the rotational and the linear quantities. So for example, your x is a replica of theta, your v is a replica of omega, and a tangential means we call it tangential because in a circle, if we have the acceleration while an object is going around in a circle, it has angular acceleration, but tangential to this acceleration, tangential to the circle is another component of the acceleration which we call a tangent. So basically the overall acceleration has 2 components. One is the radial component, which is towards the center, and one is the tangential component. So when we add them, the total acceleration comes to be the sum of these 2. But here we are not doing components. We are only trying to show that there is a dependence of linear and rotational quantities on each other. For example, theta is x over r, and which also means x is r theta, and omega is v over r, and alpha is also a tangential over r. And there's also one more quantity that we talk about, another acceleration, which is ac. That is the centripetal acceleration, which is v square over r. So it's a derived acceleration. So you can always substitute the values of v in terms of, over here we have v, so we can substitute the value of v from here. And then when we substitute that value over here, we get r square omega square over r, and one of the r goes away. That's why we can write it as r omega square, or you can also call it as omega square r. That's how it's mostly written as. So AC is the centripetal acceleration, and we use sometimes we use this also in the problems. So this is what we have covered so far, and we also did some of the problems based on these concepts. And in the office hours time today, I also touched on one or two problems that are key to understanding these rotational and linear quantities and their dependence on each other. So let's take a look at a simulation. I hope it works. This is a PHY simulation, and I think I have a window open for this, so just hold on a second. No, it's not visible, so we might as well download one. Okay, so let me do that. So downloading the Ladybug simulation. So as usual, it tells you to open. So if you go ahead, and it doesn't have an HTML website, but it just downloads. You can download the software and then play it. So it's going to open in a little while. So this is basically a scenario where we are going to understand rotational motion and try to understand what happens to the vectors also. And there are you see a green vector which is showing the linear vector, and you see the a acceleration is towards the center. So we can reset it all, and we can go ahead and see this in more detail. So basically there is a beetle and there's another creature here. If we put both of them and try to compare their motion, you can even move it ahead. You can move the beetle out. You can do anything with this ladybug and beetle. So you can select the variables that you want to see the graphs for. For example, we have theta, theta, omega, and alpha. It's a little tiny, but I'm sure you'll be able to select them. And if you want, you can also show plots of theta, omega, and v. So just play with them. And these symbols, you already know what they represent. So right now the angle is 0 and the turntable is not rotating at all. So initially it shows some motion here, but it's fine. We can reset it all and begin from the very beginning to see what happens to the variables. What do you expect will happen to the linear component of the velocity? What do you think will happen to the rotational components of the velocity? And let's see what happens when we give them certain angles. I'm choosing the second one, and then all other quantities are on. So we'll compare the vectors here. So let me give it a little turn. So now look at the vector for velocity. The velocity is the green vector for both of them. It's going tangential, and you see the acceleration that is towards the center. That's the centripetal acceleration. And if you want to see theta, omega, and these are the variables that you're looking at. You're looking at theta, omega, and a. So let's look at theta, omega, and v. So that's also the same, and theta, omega, and acceleration. So the graph represents the same. So you are able to see this. What does this graph mean? It shows that as the angle is increasing, the angle keeps on increasing, but we are not able to see it because it's rotating. So its number of rotations, theta, is changing. While the theta is changing, you can see that the velocity v for that kind of motion is not changing, and also the acceleration is also not changing. It's constant over here, right? So we can stop it or we can play back, and that's how these quantities are related. I don't think there is any better view for this one, but we'll go back to our slide and try to see what happens after that. So try to play with this simulation and try to understand the rotational quantities and their relationship with each other. How about trying a simple problem based on these again, so that we can revive what we learned and calculate the angular velocity, so you know what we are talking about, of a clock's second hand. So we have a clock and you have 3 little needles on this. One is an hour hand, one is a minute hand, one is also a second hand. So you have to find out the angular velocity with which they are going. So they all go at different rates. The hour one goes slower, the minute one is faster than the hour one, and the seconds needle is faster than the hours clock. So I'll do one of the parts here. So you're asked to find out omega, the second hand. So what is the angular velocity of a second hand? So we are trying to find out omega. When we are talking about omega, we are basically trying to find out how much time does a second's hand or a minute hand or an hour hand take to go around in one circle. So one circle means 1 rev, and 1 rev for the second's hand is 60 seconds. So we have to find the value of omega in radians, and 2 pi radians is basically 1 rev. So when you are going to work on this, you will get answer in radians per second, which represents basically your angular velocity. This is the angular velocity of, when you work on the math here, you'll get 1.05 into 10 raised by minus 1 radians per second, and this is scientific, in the scientific notation we are representing it. And similarly you can work on part B, which is asking you to find out omega for a minute hand. Again, 1 rev for a minute hand is 60 minutes, but you know you have to bring it back to seconds. Okay, so you're not done with the conversion yet. We want the answer to be in seconds, so 1 minute 60 seconds, and then you are also going to convert the revolutions or the revs to radians. So continuing 2 pi radians is 1 rev over here. Work on the math, pause my video, and then you can start working on it and do them simultaneously. So you'll get 2 pi radians divided by 3600 seconds. Are you able to see what is happening? With the increase in time, your angular velocity is decreasing. So for the minute hand, the angular velocity is 1.73 into 10 raised power minus 3 radians per second. So do not go by the first digits. 10 raised power 3 is definitely lesser than 1.05 into 10 raised power minus 1 radians per second. In the same way, you can go ahead and solve for hour hand. So omega is 1 rev over 1 hour. And here I'll do a little shortcut and I'll say 1 hour is 3660 minutes or 60 seconds. So hour hand, how many hours does it go? It's multiplied it by 12 because to complete 1 revolution, it has to go 12 times to complete the hour, 12 hours, the 12-hour revolution. I'll modify this. It's basically 1 revolution happens in 12 hours. And 1 hour has 3600 seconds. And then we are going to work on our conversion for revs, which is 2 pi radians, same thing as we have been doing, 2 pi radians over 1 rev. So the rev and rev will go away, the r and r will go away, and you have your, you can solve your 2 pi radians over 1 over rev. That becomes 1.45 into 10 to the power of minus 4 radians per second. So this is just to show that how we can convert from revs to radians, and please do practice this because you definitely will get something like that on the exam. Part 4 is very interesting. What is the angular acceleration of each of them? So will there be acceleration? Start thinking. Is the seconds needle accelerating? Is the minutes needle accelerating? Is the hour needle accelerating? If that was the case, the time would be like going crazily changing, or that is not the case though. So they all go at a constant pace. Hence, part D, there is no acceleration. For an acceleration to happen, there should be change in the angular velocity. There is no acceleration in either case. So that was a trick question. Next, we come to the most important part in chapter 8, and that talks about rotational kinematics. And rotational kinematics resembles our kinematic equations that we did for linear motion. If you remember those, in chapter 2, and 3 we were using kinematic equations like V is equal to V naught plus A into T, and we had V square equal to V naught square plus 2A x minus x naught. I'm talking about one-dimensional equations, and x is equal to x naught plus V naught T plus 1 by 2 A T square, and these were the kinematic equations. And if you remember, what is the most important thing for kinematic equations is A is constant. Only then they qualify to become kinematic equations. A has to be constant. They shouldn't be changing acceleration. A has to be constant. So similarly, for rotational kinematics, we can use the same phenomena and convert our linear kinematic equations into rotational kinematic equations. So just by using our intuition, we can begin to see how rotational quantities like theta, omega, and alpha are related to one another. For example, if a motorcycle wheel has a large angular acceleration for a fairly long time, it ends up spinning rapidly and rotates through many revolutions. So you start thinking about it. If something has larger angular acceleration, won't that keep on spinning for a long time? In more technical terms, if the wheel's angular acceleration is large for a long period of time, then final angular velocity omega and the angle of rotation theta must be large. So basically, in these kinds of scenarios, the wheel's rotational motion is exactly analogous to the fact that motorcycles' large translational acceleration produces a large final velocity, and the distance traveled will also be large. So if you're going to go, if you're on a motorcycle and you're increasing your rotational speed, it automatically your linear or the translational speed also increases, so you can go faster. So the kinematics of rotational motion describes basically the relationship among rotation angle, angular velocity, and angular acceleration and time. So we translate the equations from the linear quantities or linear kinematics to angular kinematics. So we'll look at each equation together. So if I have to use this equation, V is equal to V naught plus A into T. So we know that in rotational kinematics, we represent A as AT. Because we are talking about rotation, so we need to specify that A is basically translational or tangential component of the velocity. I'll show you one example here how we get our first equation. If you remember, we talked about relationship between V and omega, and there's a relationship between V and omega. So what do we do? V is equivalent to R into omega. Remember, we had the three equations. If we go back one slide and show you these equations. So we have V is equivalent to R omega, this one, and X is equivalent to R theta, and A tangential is equivalent to R alpha. So we basically have these equations where linear and rotational quantities are related to each other. So I'll show you conversion from how by substituting the relational quantities into this, we can get this equation. So V is basically R omega, I'm substituting, and plus your, is equivalent to R times omega naught. So we write R times omega naught. R is not changing because R is the radius. And for A, we basically write R times A, which is, R times A alpha. We have converted our A, the translational acceleration is related to rotational acceleration by this equation. So that's what we have substituted in this. Instead of writing A t, we are writing r alpha. Instead of writing v naught, we are writing r omega naught. And instead of writing v, we are writing r omega. So if you see that r and r and r is common in all of them, we take it out and cancel. They all cancel because they are everywhere. So that is why our first equation of kinematics becomes, rotational kinematics becomes like this. So that is how you do it. And same, you will substitute the same kind of x is r into theta, and you go ahead and substitute in here and here and here. And we see that if we keep on doing the same trend by substituting in the linear equation, the rotational quantities via the radius, we will get this equation. So do you see a resemblance? The first rotational kinematic equation is final angular velocity is equivalent to initial angular velocity plus angular acceleration multiplied by time. And we have the same type of equation in linear kinematics. Similarly, theta, which is the kind of a replacement for displacement or the final displacement, if we have to extend this, we can also write theta equivalent to theta naught, which is the initial position of, or the initial angle, omega naught t plus 1 by 2 alpha t square. That would be the correct way of writing it, basically. Theta naught means when you're beginning, your angle is 0. So it's okay to write it this way. And similarly, omega square is equal to omega naught square plus 2 alpha theta minus theta naught. You can also write like that because we are used to looking at these equations as final minus initial. And lastly, if you remember in kinematics, we had a fourth equation which we very sparsely use, where we say that average velocity is equivalent to the sum of initial and final velocity divided by 2, but that's the average. But this happens only in those cases where A is constant. Similarly, we can translate the same equation into rotational kinematics by saying that average angular velocity is equivalent to final angular velocity plus initial angular velocity divided by time, because alpha is constant. I hope you understood the relationship between these quantities. So we go ahead and now solve some problems based on what we have learned just now. And this is the final section we are picking up from this chapter. We are not proceeding into other bigger quantities since we do not have that much time. We might as well perfect what we are learning here in these two sections. Okay, so erasing all of this, now you have a neat formula sheet here. So you can now work on the problems. So we have basically a rotating merry-go-round makes one complete revolution in 4.0 seconds. You can go and check the figure in the book. What is the linear speed of a child seated 1.2 meters from the center? So rotational motion is experienced in merry-go-rounds, in Ferris wheel, and in microwaves, in blenders, and everywhere, wherever there is rotational motion involved. So the child is seated 1.2 meters away from the center, and it makes one complete revolution in 4.0 seconds. And you are asked to find out what, and there are two things you are finding. What is the linear speed? You have to find v. And you also have to find out what is her acceleration. So you have to give a. That means you have to find out its at and its ar, both the components. So do we know omega? Do we have omega? So we have to understand what is omega. Omega is basically 2 pi radians. So 1 revolution, that means 2 pi radians, okay, is covered in 4.0 seconds. So although he's not saying he's giving you the angular velocity, but you can always understand that he's telling you 1 complete revolution. 1 complete revolution is 2 pi radians. That is 1 rev. Okay. You could also do this other way by writing 1 rev over 4.0 seconds and then convert it into radians per second. So you can do this way: 1 revolution over 4.0 seconds. 4.0 seconds, right? And you convert the rev to 2 radians. 2 pi radians over 1 rev. So it's the same thing. But if you like to see all the steps, that's how I would suggest you do: 2 pi radians over 4.0 seconds. Then that is your omega. And that comes out to be 1.57 radians per second. All right. Now we know there's a relationship between V and R and omega. So I can find out my tangential velocity, because he said velocity, not angular velocity. He said linear speed. So you can find it with the help of this equation. R is given, the radius is 1.2 meters. That's the position where the child is sitting, multiplied by the omega, which is 1.57 radians per second. All right. So when you work on this math, you should get close to 1.9 meters per second. Now you'll be wondering, how did you get meters per second? There's a radian also. The radian is a dimensionless quantity I mentioned in the office hours today when I was doing the problems similar like this. So if you are finding V, you can blindly write radians per second if you have converted from revs to radians. So do not worry about radian part of it. Next, B, you have to find what is her acceleration. So you're basically finding out AR. So the acceleration is radial. He's going in a merry-go-round and the object is not tangentially going out. So there is no tangential acceleration. AT is not existing, but there is a radial acceleration because he continues to stay in the circle. So the radial acceleration is omega square over r, omega square r. We also call this as centripetal acceleration. So omega square r. So we already know what is omega. We can substitute that 1.57 radians per second whole squared multiplied by r is already given to you as 1.2 meters. And since this is AC, not alpha, your units will be meter per second square. So once you work on the math, it comes out to be 3.0 meters per second square towards the center, because we are talking about centripetal or the radial. Okay, so that solves your problem for this one. So let's look at one more problem. Calculate the angular velocity of Earth. This is an interesting problem because now we can apply our knowledge of rotational motion to finding velocity of Earth, finding velocity of Earth around the sun and about its axis. So you know that Earth spins on its axis. Let's find out what happens to the speed. So the Earth makes one orbit around the sun in 1 year. So Earth goes around sun in 1 year. And do you know what is the distance? Well, if this is my sun and I'm going around it, I start from here, so I have completed 1 revolution. So I can easily say the orbital speed, angular speed of Earth around Sun is delta theta over delta t. What is theta? Is one revolution over 1 year, right? But I can't keep the values like this. I have to find out their conversions. So 1 rev is 2 pi radians, and 1 rev for 1 year. I have to go and solve this for units in time, okay, in seconds. So for 1 year, I'll write down the year should get cancelled. 1 year, 365 days. But I can't keep the days. Okay, so 1 day, 24 hours. See, this is an interesting problem. And 1 hour, 60 minutes. And 1 minute, 60 seconds. And that's it. We'll stop here. So you can see the rev goes away, the rev goes here away. Did the year go away? The year goes away with this. The day goes away with this. The hour goes away with this. The minute goes away with this. And we are in the end left with 60 seconds. So if you go ahead and solve this, it will be 2 pi radians divided by 24 multiplied by 60 multiplied by 60. There was a 365 somewhere. Yeah, there is, multiplied by 365. Okay, that's the most important part. So that is the orbital speed. Go ahead and plug this all in your calculator and solve this. Basically, this time comes out to be equivalent to 1 year is basically 3.16 into 10 raised per 7 seconds. So that comes out to be 2 pi radians. 2 pi radians divided by the multiplication of all of this is a big huge number, 3.16 into 10 raised per 7 seconds. These are the number of seconds in 1 year, and you'll get radians per second as unit. When you work on it, you get 1.99 to the power of 7 radians per second. That's not a lot of velocity around the sun. In the same way, you can find out how much is the angular speed of Earth on its own axis. So how much time does it take for Earth to spin on its axis? That creates day and night. So 1 day. So that's called rotation. Okay, rotation, Earth rotates on its axis once in a day, like it takes 24 hours. Rotation, again delta theta over delta t. What is your delta theta? I'll say 2 pi radians, which is basically 1 rev. You can go ahead and solve, first write down 1 rev over 2 pi radians in 1 day. But I can't leave it like a day. 2 pi radians are correct. That is basically 1 rev. And for the day, I need to substitute 1 day, again 24 hours, and then you can go ahead and talk about 1 hour, 60 minutes, and then you can go ahead and say 1 minute, 60 seconds. And when you solve this, you should be able to get for this entire thing, it is 86,400 seconds, sorry, in a day. All right, so when you solve all of this, you'll get slightly higher value for the speed because it's happening every day. So naturally, it's going to be more than what speed that we have going around sun. So omega of rotation can be solved like this. I think this is an interesting problem because it makes us realize how slow we are moving around. Then comes an equally interesting problem. We have 3 or 4 problems to go still, and this one is a very special problem because it has many parts, and it's slightly complicated, but that's why I'm going to explain it here. So there's a 61 centimeter diameter wheel which accelerates uniformly, all right, about its center. So there is uniform acceleration now. We are talking about rotational kinematics now. So rotational kinematics. So we learned the formulas for that, and it's rotating around the center from 120 revs per minute to 280 revs per minute in 4.0 seconds. So you know that omega naught and omega is given. Determine its angular acceleration. You can find that using rotational kinematics. The radial and the tangential component of linear acceleration of a point on the edge of the wheel 2.0 seconds after it has started accelerating. So first of all, we are going to convert the rev values. We are going to convert omega naught, that is 120 revs per minute, into radians per second. So you know the drill, 2 pi radians over 1 rev. And for the minute, you know we are going to substitute 1 minute over 60 seconds and go ahead and solve its radian per second value. So 12.57 radians per second, sorry, not meters per second. This is angular velocity, not linear velocity. Then we go ahead and convert omega. 280 revs per minute can be converted in a similar way by putting 2 pi radians over here and 1 rev. Again, 1 minute, 60 seconds, and that's equivalent to 29.32 radians per second. Now we have all the quantities, and we'll go ahead and solve for the first part. So part A is asking to find out angular acceleration. So we know omega is equivalent to omega naught plus alpha times t. All right, so substituting, or we can rearrange and write it as alpha is equivalent to omega minus omega naught, omega minus omega naught over t. Go ahead and substitute the values that you found behind. 29.32 minus 12.57 that we previously found divided by time was given as 4.0 seconds. When we plug in these values in the calculator, your alpha comes out to be 4.188 radians per second square, which can be written in 2 sig figs as 4.2 radians per second. All right, that was part A. Now part B asks us to find the components of acceleration. Components of acceleration. So basically we are finding a tangential, and we are also finding alpha after some time. So to find the components of acceleration, the instantaneous angular velocity is needed. We need to find instantaneous angular velocity. And how do we find the instantaneous angular velocity? So basically omega is equivalent to omega naught plus alpha into t. So the initial velocity is fine, but we know our alpha, which is constant, and time is also given, so we can find out what is happening after 2 seconds. Time is 2 seconds, so we go ahead and substitute the values. We have 12.57 radians per second plus, for alpha you can put 4.188. I would suggest using this value because that will give you a better answer for radians per second square, some acceleration, and multiplied by time as 2.0 seconds. So if you look at what B part is asking you, in B part it's asking you what is the radial and tangential component of linear acceleration of a point on the edge of the wheel 2.0 second after it has started accelerating. So it won't, the final or the angular velocity at that time will be different. So that's why we were forced to find out for 2 seconds what is going to be the angular velocity. So when we worked on this number, we get the instantaneous value for it as 20.95. Leave it like that, don't approximate it, radians per second. And then the radial component of the acceleration, which is also AC, is equivalent to omega squared r. So r is given. If you look at it, let's read the question again. A 61 centimeter diameter wheel. So remember, students often make this mistake. You are not talking about diameter, you need a radius. So you divide this, it's 0.61. If you're converting into meters, divided by 2 is the radius. So be very careful to read the problem carefully. So then go ahead and substitute 20.95 radians per second whole squared 0.61 meters over 2 because the diameter was given. When you multiply this, pause your video here and then go ahead and start solving. And 130 meters per second square is the radial acceleration. So we are finding components of the acceleration. Next we find A tangential. So A tangential is easy to find. It is alpha into r. Alpha is already given to us. We found it, 4.22, but do not substitute 4.22, substitute 4.188 to get a better approximation. Multiply by r, where r is again 0.61 meters over 2. You're free to divide it beforehand and keep it ready, or substitute it here itself. The choice is yours. So once you work on it, this becomes 1.3 meters per second square. So this tells you that the tangential acceleration is far, far less compared to the radial acceleration, which is 130 meters per second square. Similarly, we have problem number 17, which talks about an automobile engine slows down from 3,500 revs per minute to 1,200 revs per minute in 2.5 seconds. Underline the word slows. So that means there must be a negative acceleration, negative angular acceleration. Its angular acceleration needs to be found. which is assumed to be constant. When we say that angular acceleration is constant, you're again looking at rotational kinematic equations. The total number of revolutions need to be found that the engine makes. So you have to find out how many times is it rotating. So an interesting problem for part 1. For part A, let's begin it here. Trying to change the color. I'm bored of red color. Okay, so part A is for constant angular acceleration. So basically you are going to first, I would suggest first convert your omega naught, which is 3500 revs per minute, into its radian per second counterpart. Same, do it for final radial rotational velocity, 1200 rpm. Convert it into its radians per second value, and you can either do it that way, keep the values ready, and then use rotational kinematic equation. Omega is equal to omega naught plus alpha into t, and get your alpha from here, which is omega minus omega naught over t. So since I'm not solving it in steps like you are going to do, I have kept the values in the same place. I wrote down 1200 revs per minute. I'll convert in the end, but you can choose your own style. Normally it's better to convert them first and then substitute. I'll leave the exercise of conversion for you to do. And we have time is given as 2.5 seconds. So we basically get minus 2300 revs per minute divided by 2.5 seconds. Now I can't keep this rev and seconds like this, so we need to convert the units. Minus 2300 revs per minute instead of rev per minute. This is alpha, so remember there is a second already here, so we'll not touch that s. The second, we'll convert the rev per minute to radians per second, and 2 pi radians, you already know the drill, is 1 rev, and 1 minute 60 seconds. So you see you are going to get radians per second square. You have second here, you have second here, that's going to get squared, and rev is going to get cancelled. So you have minus 2300 multiplied by 2 pi radians divided by 60 second square. That will give you the final answer as radians per second square. Did I miss 2.5? Oh yeah, there's 2.5 as well here, and there's 2.5 here as well. So go ahead and solve this now, and you'll be able to see that you get the value as minus 96 radians per second square. The minus tells you that it's slowing down. So there's a lot of conversion to do. So I would suggest not to do it this way, the way I did. I was feeling kind of lazy to get omega naught and omega done beforehand, but it is always good idea to get the values first and then substitute them. See how complicated it became when I did everything in one step. Okay, so my suggestion to you is not to do it this way. Always break up your problem into simpler steps. Then we go ahead and solve the B part of this, and the B part asks us to find out the angular displacement. So basically we have to find out theta. Angular displacement, we assume that, again, these are rotational kinematics. We assume alpha to be constant. Okay, and we can use any of these equations can give us, if you look at, we have theta is equal to theta naught plus omega naught into t plus 1 by 2 alpha t squared. You can even use this to get the angular displacement. Or there is one more equation for theta that you can use. You can go ahead and substitute the value in this one. This is easier to do. We have the alpha as constant. We already know this value. Do we have time? 2.5 seconds. We can use that. Find the total number of revolutions. So once you substitute, theta naught can be taken as 0. Omega naught, you already know what the value for it is, 3500. And then go ahead and find theta. So I will leave this part for you to do. You can work on it and get the value as theta, the number of revolutions, comes out to be 98 revs. So please work on this part. 98 revs. Okay, so if you still have some questions about how I got this, you can meet me in the office hours on Tuesday, or you can shoot out an email. So next is the problem number 18. So a centrifuge accelerates uniformly from rest to 1500 revs per minute in 240 seconds. How many revolutions did it turn in this time? So basically we are asking you to find theta. We can do the same way that we did it in the previous question. We also know that omega, average angular velocity, is delta theta over delta t. You can use the same thing here as well. You can say that delta theta over delta t is equivalent to average velocity and average velocity when acceleration is constant is given by initial. You can simply say theta over t is given by omega plus omega naught over t2. You can use this equation also to get theta. So theta is theta minus theta naught, and we simply write t for this. That will be omega plus omega naught over 2. This condition is only true when alpha is constant. Okay, so you can do it this way as well and get theta. Theta naught can be taken as 0. Therefore your theta will be equivalent to t times, right? So you multiply it, omega plus omega naught over 2. I think this is a better way, and you should be able to get 98 revs using this method. Similarly, now for this one, we'll use the same scenario. We'll say that, okay, this can also be written as theta minus theta naught over t, because we always say t minus t naught, where t naught is considered 0. So which implies you can write this one as well, equivalent to omega plus omega naught over 2, which is nothing but average angular velocity. Again, this happens when alpha is constant. That means it's rotational kinematic equation that we use. Accelerates uniformly has a meaning from rest to 1500 revs. So this one is already given as 0. We have omega naught as 0. So we just, because it's starting from rest, rearrange the terms and you'll get theta is equal to, theta naught can be also treated as 0 because it starts when we are beginning, angle is 0. So it is t times omega by 2 because rest of the terms became 0. So your t is 240 seconds. Again, I should have converted the unit beforehand, but I'll do it in this step for you right now. But I would suggest you all should first convert the unit from rev per minute to radians per second. We have done it already many times, so I'm sure you'll be able to solve it now. We have 0 for the final initial, so we just have 15,000 revs per minute. Revs per minute. So you must remember the end result for the units for theta should only be radians. Okay, or you can also keep it in revs, that's also fine. I'll basically convert this 240 seconds, I'll keep like that, but 1500 revs, 15,000 revs, I'll keep them just like that. It's not necessary to have radian value for this. We can either leave them in the revs because all we are doing is finding how many times did it go. So revolutions makes more sense. So we'll have 240 multiplied by 15,000 revs. And that's what I was expecting. I didn't want time in the equation because this is a displacement equation. It's the angular displacement. And that is why the answer will not have divided by t, divided by time. So when you work on this scientifically, you can write it as 3.0 into 10 raised power 4 revs. So that is how many times it has gone. If you go to that FET simulation, you can see that the angle keeps on going on and on and on. In that simulation, that's because the revolutions continue while you are going. Imagine you're going from Bedford campus to your home, and how many times your wheel must have rotated, how many revs it must have taken to take you to the from college to home. So that's definitely a decent number, 3 cross 10 raised power 4 revs in a time of 240 seconds, which is like how many minutes that will be. So we'll work on our last problem now, and then we'll call it a day, and that's the end of the chapter. But watch out for more content coming in the office hours. So there's a cooling fan and it's turned off when it is running at 850 revs per minute. It turns 1250 revolutions before it comes to a stop. So that means it had gone how many times? The theta must have been 1250 revs. So what was the fan's angular acceleration? Assumed constant. So you have to find the angular acceleration, that is alpha. How long did it take the fan to come to a complete stop? So basically we are trying to find out, first we are finding alpha, okay, and then we are finding time. Okay, what is given to us? We are given 850 revs per minute. A cooling fan is turned off when it is running at 850 revs per minute. So basically we can say that, okay, we turned it off. This omega naught is now the new beginning for it, 850 revs per minute. Convert your answer into radians per second, okay? Find the conversion even if I'm not doing it. And then you have what else is given? Because we are bringing it to stop, so final must be 0 radians per second, because that's the objective. We want the cooling fan to stop. That's why we are turning it off. And what else is given? We have been given revolutions, so that means theta is given as 1250 revs. 1250 revs. It may be a good idea not to convert it yet, because if you convert them into 2 pi radians, it will be a very big number. So we will convert in the end. Okay, so let's go to the next page and solve the problem. So first of all, we'll find alpha, the angular acceleration. That is given by, if you look at the rotational kinematic equations, there are many equations given. Out of them, there is one which is given as final angular speed square minus plus 2 alpha theta minus theta naught, where theta naught is the initial angle, so I'll treat it as 0. This is one of the kinematic equations which resembles v square equivalent to v naught square plus 2a x minus x naught. Okay, so this is in the rotational form and this is in the linear form. So we looked at them. You have a table where you have all these equations and you'll be given a formula sheet. So rearranging this equation now using omega square equivalent to omega naught square plus 2 alpha theta, assuming theta naught is 0, 2 alpha theta. Go ahead and find out alpha. So subtracting omega naught square on each side, which is 2 alpha theta. And then in the next step, divide both sides by 2 alpha, because 2 theta, I just want alpha out. So I want to find out alpha. So therefore divide both sides by 2 theta. We have omega square minus omega naught square divided by 2 theta is equivalent to alpha. So now I'm going to substitute the values in here. And I know that the final angular velocity is 0 and the initial one is given as 850 revs per minute whole square. I deliberately didn't convert because my theta is also given in revs, so I'll keep it for now, and towards end then I'll convert it 2 times, and it's saying it moved. The angular displacement was 1250 revs. So when our alpha should be radians per second square, so we'll do that towards the end. So when we look into this, the math part of it, we get minus, when you work on 850 divided by 2 cross 1250, you get 289 rev square, and one rev cancels because there's a square here, so you get rev per minute square. And I want to convert it into radians per second. So 1 rev 2 pi radians, so the rev is taken care of, but minute square, I want second square for that. So 1 minute over 60 seconds whole squared. Don't forget the whole square thing because you're squaring the entire term. Now your rev is gone, your rev is gone, your minute square is gone, and the minute square will go away with this. You are left with minus 289 into 2 pi radians divided by your 60 cross 60, that is 306,000 seconds square. Please take out your calculators and work on this number. That's equivalent to, now the value comes out to be minus 0.50 radians per second square. This is simply our alpha. I guess the mathematical calculation is more than the other. Basically, it's a simple problem where you're just picking the formula, but the conversions are more for this one. So then we go ahead and solve for part B. Part B says the time it took to stop. How much time did it take to stop it from moving further? How long did the fan take to come to a complete halt? So I basically use the same equation that I used before, where we say that theta is equivalent to, or delta theta over delta t is equivalent to average velocity, average angular velocity, which is nothing but omega plus omega naught over t2. I can solve it this way. There is another way as well. You can solve with other equations as well to find the time, which implies I can write down theta for this simply because theta minus theta naught is delta theta. Theta naught is 0 and delta t can be written as, so you can basically write it as theta minus theta naught over t minus t naught. We know what we're talking about here. It's omega plus omega over 2. All right, theta naught is 0, t naught is 0, so it's basically theta over t is equivalent to omega plus omega naught over 2. All right, so now you are asked to find out t. So we need to flip this. I hope I have another page here. Okay, so if you rearrange these terms, go ahead and rearrange. I might be doing this over here because I'm running out of space. Okay, so let's go here. We have more space here. So rearrange the term, multiply both sides by t. We'll get theta equivalent to omega plus omega naught divided by 2 and multiplied by t. Now go ahead and we have to isolate this. So we'll divide both sides by 2 over omega plus omega naught. This entire thing, we need to flip it. So multiply both sides, divide both sides by this term. Right? If we divide by this term, so what will we get? We get t is equivalent to 2 times theta divided by omega plus omega naught plus, please work on this conversion and then substitute for theta. You have 2 times 1250 revs, all right, and divided by omega plus omega naught. Omega is 0, omega naught is already known, it's 850 revs per minute. Again, go ahead and since I'm running out of space, go ahead and rework on the revs per minute conversion. The rev and rev is actually going to go because in time we don't need rev. The minutes can be converted to seconds, so you will get basically close to 176.5 seconds. It takes so many seconds for the fan to come to a halt. And when you get my solutions, you can work on these problems further. So the solutions will be posted ASAP after you submit the homework problems. Okay. So this is it. And chapter 8, we only did 2 sections. section 1 and section 2. You do not need to look into any more of the sections because this chapter is pretty long and we will not be able to complete. Rotational kinetic energy, angular momentum, and many other things that you saw in actual force and dynamics before you went into rotational motion. Any of these quantities that you saw in linear motion are also seen in rotational motion, and they have new names. Like for example, we have for mass in rotational motion, we have moment of inertia. Denoted by I. And just like we have kinetic energy in our translational motion, we have 1/2 I omega square as the rotational kinetic energy. Since we are not doing these, it's a good idea I show you some of the formulas. And then we also have angular momentum. It's denoted by L, and it's I. Angular momentum I is denoted by L. So this, if we had one more week, we would have been able to do it. But since next week is our last week and we have to do the review as well, so I may not be able to get into all these problems. So angular momentum is represented by L, and it's equivalent to I into omega, where omega is the angular velocity, I is the moment of inertia, which is a replica of mass. If you remember, you did linear momentum as P is equal to m into v, where m was mass and v is the velocity. So it's kind of similar. And if you look at kinetic energy for your translational kinetic energy, it is 1/2 mv square, which resembles the rotational one. Omega square and v square are replicas. So there are similar quantities. If we had been able to finish the chapter, we would have looked into all the other facets. Also there is torque, which is force. Rotational torque is the rotational force. So it has the same job as force. So it's force times distance, or it's the force into the lever arm. So we will not be able to complete that. Just do the 2 sections and we will be fine for finals.